So I'm here at the cosmic streams in the era of the Vera Rubin Observatory in Puerto Varas, Chile, on a cloudy day. It's been off and on sun, and we've been talking about stellar physics. And I'm here with Riley Clarke, who is a doctoral student. He's working on his thesis, and he presented the paper here earlier this week on part of his work. And he's at the University of Delaware in Newark. And how far along are you actually with your thesis?
I'm in the 6th year of my PhD program.
Good, gosh, it takes that long.
Yes, yeah. In the U.S., it takes a little bit longer. And so, yeah, we're very close to submitting the first paper of that thesis, and I'll probably be writing 1 to 2 more as part of that work.
And you actually gave a very interesting talk on how we can use one-off images from the Vera Rubin Observatory, the LSST, and it's the upcoming telescope that's going to revolutionize transient astronomy. And your focus is on flaring, stellar flares from red dwarfs.
That's right.
And red dwarfs, from an astrobiological, let's just put it like this. 70% of all stars in the universe are red dwarfs. They live a hell of a long time.
Yep.
They are candidates for life. Astrobiologists are, salivating over them left, right, and center. But these stellar flares, we don't really know the rate of the stellar flares so much, or the temperatures. And you have come up with a unique way to use one-off images.
Right.
That you don't have to follow up with a second telescope to be able to extract information, correct?
Yeah.
Tell us about that.
Sure. So the stellar flares are very short duration transients. So the median time scale of these events is about 30 minutes. And they're also it's impossible for us to predict when they're going to happen. We call this that they're stochastic in nature. Random, essentially. And so what that means is that makes them a very challenging target for most astrophysical surveys that might only observe the same star once every 3 days in in one filter. So what that means is that if you do capture a flare, it's only going to be captured in a single image. And which means that we can't really do the same type of flare studies that were done by other space telescopes like Kepler, which took a picture every 2 minutes in its fast cadence mode. So that means we can't do that same type of science with Rubin unless we develop a methodology to extract information from an event that's only captured in one image. And the way we think we can do that is by using the refractive properties of our atmosphere to infer the temperature of a stellar flare based on how much the star moves on the sky during that event, because sources actually move when sources are refracted by the atmosphere, and so their position on the sky depends on their color. And
this, in the same way that when you look into a body of water, a clear body of water, either a lake or a swimming pool, you see objects refracted.
Exactly. Or when you look at a straw in a glass of water,
exactly.
It appears offset.
Perfect.
Yeah.
Okay. And so over the course of the Rubin 10-year time frame, or 5 to 10 years, whatever it is, I think you're going to observe 3 million of these flares.
Yes, that's what we expect.
All from red dwarfs.
Not mostly from M dwarfs, from red dwarfs, but
from
also
M
from
dwarfs.
some other types of stars too.
From other types of stars, but you particularly interested in the M dwarfs.
Yeah, because most of them will come from M dwarfs, and M dwarfs are also flares are easier to see when they happen on M dwarfs.
And tell us why that is.
Yeah, so so what we call the visibility of the flare is the contrast between the part of the star's surface that gets heated and the rest of the star. So on an M dwarf, you have a very cool red photosphere,
right?
And then when you have a flare, it creates a really hot blue region on the surface. And so that way you have a lot of contrast between the flaring region and the rest of the star. When you have a hotter star like our sun, like a G-type,
Right.
there's not as much contrast between the flaring region and the photosphere because the photosphere is hotter.
Right.
Hotter and more yellow and than compared to an M dwarf.
And the actual temperature is like 50% higher, you said, or 100% higher than it normally is?
Yeah, the kind of canonical assumption, the general assumption of the flare temperature would be like that they're all about 10,000 Kelvin. The surface of our sun is about 6,000, so
quite a bit higher.
Yeah, quite a bit higher.
I'd say. And so the reason these red dwarfs are interesting for astrobiologists is because they think that if planets orbit close enough to the red dwarf, they could possibly be habitable. And we had that recent debate about the TRAPPIST system, which I think there were 7 planets, incredibly terrestrial, and there's still a lot of argument about whether any of them are habitable. But I think the conclusion is that none of them are habitable at this point. That's the conclusion. But you brought up something just now in the interview that these these stars, the flaring could actually enable life, and counterintuitively. Tell us about that.
Yeah, so this was a study that came out just a couple years ago, where they used observations of M dwarfs that were taken by the Kepler Space Telescope.
Right.
And they concluded that there's, for particular combinations of the rates of flares and the energy of the flare, so flares of a given energy will occur at different rates, and that for particular combinations of the energy and flare rate, it's actually possible that the energy from a flare, especially the ultraviolet flux, the ultraviolet light that's produced, could enrich prebiotic chemistry and provide an energy input to early prebiotic processes,
and enable
essentially enable the development of life on
the onset
planets.
of microbial life.
Exactly.
And the other interesting thing is that you mentioned that if once life has started on one of these planets, it's not likely, not to put words in your mouth, that flaring from the same star will wipe the life it's enabled out.
Yeah. So my thoughts on that is that over a star's lifetime, the stars tend to flare more when they're very young,
Right.
and then as the star ages, the rotation slows thanks to something we call magnetic braking.
Right.
And so it spins down over time, and as the rotation slows, the magnetic field weakens, and flares are magnetic phenomena. So as the magnetic field weakens, flares happen less often and with lesser energies. So I would expect that as a star, as the planet around an M dwarf, as the star ages, the flare rates will go down, and so the planet will be at less risk of ozone depletion from a flare at later times.
Okay. So, but you remain agnostic. You told me that you were really interested in the stellar physics. You like stars, regardless of whether there's life on planets circling them.
This is all with the caveat that I am not an astrobiologist by any means. I am definitely a stellar astrophysicist.
Okay. Well, listen, we thank you for your time, and it's Riley Clarke, University of Delaware. Thank you for your time, and did a great job with the talk.
Yeah, thanks. This was fun.